Test 1 2 3. Test 1 2 3. Testing 1 2 3. Microphone, microphone. And we are live. Let's see if I can get a copy of the actual stream up so I can just check the live nature of the stream. There it is, live now. Double click. That'll be very distracting when I see that, I'm sure. But I'm curious nevertheless. So I'm actually having a chance to see the live stream, which is delayed significantly. I wonder how much delayed it is. Let's count. Let's count how and see how delayed the actual stream is. I'm going to start writing numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, holy crap, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, roughly 30 seconds, 31, 32, 33, wait a minute. Wait a minute, that didn't work. I think what happened is I lost track of my numbers. Well, anyway. So I'm trying to figure out, so I think I've got this down. I've figured out I'm somewhere at about 30 seconds of delay. All right, fair enough. So what I'm going to do for this lecture series, welcome aboard let's see, I'm going to get everybody's name correct. Ovechkin. I was counting because I was trying to calculate I was doing the roughest possible way of figuring out the stream delay. So what we're going to do today is we are going to do a lesson on the one-dimensional wave equation. So I'm going to actually try to record that live and just do a few takes on it. And then this will be integrated into this sort of theory of music project that we're working on. So the idea is the 1D wave equation. So a rough plan here is on the board I'm going to sketch out a little piece of string. I'm going to sort of establish that this one side of the string is located at x, the other side is located at x plus delta x. And then I'm going to point out that the tension on the string is always tangent to its direction, which is one of the fundamental approximations of the 1D wave equation. And then I'm going to assert that the angle over here is theta of x plus delta x, I guess. And then the angle over here I'm going to say is theta of x. And then I guess what we'll do is we will simply construct the overall force equations, right? So I guess what let's see, how does this work? We say T times let's see, we want the horizontal forces to balance, right? So we will say T times what? Cosine of theta of x plus delta x is the force, horizontal force over here. And over this side it's minus T times, let's see, we got that angle there, and those two angles are going to equal. So minus T cosine of theta of x. And then those two will be equal. Now, of course, we're introducing the assumption that theta is a very, very small angle, so these two guys are equal to 1, right? I'll even probably use some color there when I cross things out. And so all the motion is in the up and down, right? So, oh yeah, there's other things too, is the string has some mass density mu, and then the mass of the string is going to be the mass density mu times delta x, right? Delta x. And let's see. Well, double helix, you mentioned you mentioned about normalizing the string to length 1. Not a bad idea. I probably will not go dimensionless with this, mostly because one of the target audiences are guitarists and musicians in general, but mostly guitarists. And guitarists know all about their units, believe it or not. You could be the most complete metalhead, and you know that strings have a certain gauge, and you know that the scale length of your guitar is 25.5 inches or 24, depending on, you know, do I play a Les Paul style or a Fender style. So they love these numbers. So I think I'm going to stick with the numbers. So let's see. But anyway, I need the mass density of this thing. So I then have to say that the mass, which would be mu delta x, times the acceleration, which we have to presume is vertical. So let's see, what would I do for that? I would have to say the acceleration, I guess, is, I guess we will call the displacement, the acceleration displacement y. So y, second derivative. That's going to have to be the difference in these two vertical tensions, which is going to be the tension times the sine of x plus delta x. Let's say, I guess the positive direction will be up, right? Positive direction will be up, so this will be then minus t times the sine, not x plus delta x, sine of theta of x. See, I gotta make sure I'm ready to do this by doing a quick walkthrough here. Sine of theta of x plus delta x minus t times the sine of theta of x, right? And then what's the next step? The next step, I think, is saying you take out the t, and then what you get is, so let's see, do I have the units? Do I have everything right here? This is an acceleration, a mass times an acceleration, and this side is a force. Okay, so we're good so far. Yeah, because what's going to happen is this we're going to divide through by this delta x and form a derivative, right? So then we write t, and we say sine of theta at x plus delta x minus sine of theta at x. Then we use the small angle approximation, right? Because we've got to assume that these angles are, that there's not a lot of severe movement. Our string isn't doing stuff like this. We're assuming all these angles are really small. Although, let me think. You know, in principle, there's really no reason why this can't be part of the wave equation. I think the small angle idea, well, of course, it's just to keep it all linear, right? That's the whole point. So anyway, this ends up becoming t of theta x plus delta x minus theta of x. But the angle here, the angle of theta, that is the tangent of the curve, right? That's the first derivative of x. Why am I introducing y here? Why did I do that? Why did I do that? Yeah, so y is the vertical, of course. Y is the vertical displacement, of course. So then this tangent, but the tangent is the first derivative. So this is t times dy dx evaluated at x plus delta x minus dy dx evaluated at x. and then we divide through by the delta x, right? The delta x, and then this ultimately is equal to the second derivative of y with respect to x. So this becomes d squared y dx squared times the tension. And then you divide through by mu, and you end up with y double dot equals dy squared dx squared times t over the mass density. And that is the one. Okay, so I think I'm ready to do this. So now, having reviewed this all, having reviewed it all, I think I can produce a small, short little lesson on this subject. One of the important points to get into that I can't forget is I want to then break down all the approximations that we use that make this an ideal string. For example, here I show that the string has some, let me see, is my volume good here? I gotta check, I keep checking the screen to see if my volume's good. So here I show that the string has thickness, but the thickness of course implies that there is a cross-sectional area, and the string's obviously got mass and is made of some material, which would imply some sort of moment of inertia, right? Some sort of moment of inertia. It probably has some sort of Young's modulus, so it's going to have some sort of bending, resistance to bending, and we've got to eliminate that, right? So the string is going to be infinitely thin in the end, so there's no resistance to bending. These angles are all going to be small. Let me use another color. These angles are all going to be small, so we keep the equation linear. There's also a presumption that that the motion is all just up and down, right? That's an important presumption. So that allows us to balance t in the x direction. That's pretty important. But that, of course, is driven by the small angle approximation, right? Because cosine theta x and cosine theta x plus delta x, if this angle is small, those cosines are both going to be 1. So the force in that direction will naturally cancel in the small angle approximation. And, you know, there's other things in there, like there's energy dissipation through the bending of the string. I guess that's another thing we have to assume, is we have to assume that the length of the string L doesn't change. And you'll notice that L, by the way, you mentioned this double helix about normalizing the string length to 1. In the derivation of the one-dimensional wave equation, you don't the length of the string doesn't show up at all, right? The mass density does. The mass per unit length shows up. But when we actually solve the equation, then of course we will have fixed boundary conditions, because it's a guitar, right? So we're going to have fixed at the nut and fixed at the base, and then some initial shape of the string before it's released. And that'll be, I'll try to get that lesson done today too. Okay, so with this in mind, I'm ready to start, I think. Let me have a look here. Let's erase all of this. Well, yeah, there's no reason to keep all of this out. Erase all the ink. You can't see this, but this software that I'm using is called Vittle. People often ask what software I use. This software is called Vittle. And there's a few others out there that do what Vittle does, but I'm just comfortable with Vittle by now, so I have this sort of brand loyalty. But it's got this neat feature. It's hard to see, but let me if I put a square here, I can take Vittle and I can move it. This is how big the screen is, actually. You can kind of see by how much I move the square around. This is like the lower limit, and then I have this massive screen here. The other software only has this much screen to work with, and if you want more, you've got to change to a whole nother screen, right? And here's a whole nother screen where I can move it around. So I like Vittle for that reason. I think there are a few features Vittle does not have, but Vittle also has some really great editing features. I'll show you here in a second if I record. This is not a promotion for Vittle. I am not sponsored by Vittle, but I do. People do ask what it's used. Right now I'm recording. You can't see the recording. I guess I cut it off Well, that's interesting. Vittle seems to know about casting because it's only casting its screen. It's not casting the little controls I have. But let's see what happens if I stop my recording. I just did a little test recording, and I go into the View menu. You now see that a scene pops up here in the View menu. Now, so now I'm going to experiment with something else. I'm going to go to my Presentify, and I'm going to highlight the cursor, and I'm going to see if how would this work? Oh yeah, you can't see the cursor at all because I'm not displaying my screen. I'm still working on getting some of the equipment bugs out, but there's no way that I can show you what's going on with this circle. Like right now, it looks to me like Vittle is not casting the editorial section, so you can't literally see me edit Vittle, which is no fun, right? Some of this is I want those of you who care, I want you to sort of see how this is produced. So the way I would have to change that is, let me see, hold on a second. I would have to change that by moving the Vittle screen into my main display and then activating the display capture, and no, well, now I can at least point to things, right? But it still doesn't show what's literally going on the iPad. Huh. That's kind of annoying. That's too bad. I'm disappointed, actually. I'm disappointed, right? Like I can point to the screen here. Let me see if I can figure this out. I can point to the screen here so I can make movement. I can enlarge this, I think, so you can see the whole thing, right? And now I can point, but that's really not very helpful because I can point on Vittle anyway, right? I mean, I can use this to sort of point on Vittle, although I notice that it's stalling out a little bit. It's stalling out a little bit, so it's not smoothly showing you. Of course, I can't see. I'm trying to wait like 30 seconds so I can see how it shows up on YouTube, and I can determine whether it's this. No, it actually is. I'm watching the YouTube. Yeah, it sort of stalls out a little bit. It's interesting. I'm gonna have to. I'm gonna finish trying this. GoodNotes. Oh, I got a suggestion. GoodNotes 5 is a great alternative. I wonder, is that entirely based on the Mac itself? Because I really like using this software on my iPad. Well, anyway, this isn't a big deal. I'm going to go back to just casting the. I'm just going to go ahead and cast this and then create. I can fit it to the screen. All right. Okay, so let's go ahead and begin. Let's go ahead and begin this. And let's see, I'm going to start with just give myself a little room. All right, so when I start this, I'll probably not stop. Well, I can stop anytime, but for those of you who are in the chat watching, forgive me if I ignore you. All right, so let's start by just writing down what we're gonna do. The 1D. No. Remember, this is for guitarists, right? We'll call it the physics of a guitar string. Physics of a guitar string. Right? That's not hard to do. That looks good. Now, the point of this, by the way, is this will never be, just so you understand the context, this will never be a lesson that will just be posted like the lessons that you guys are familiar with about more graduate level subjects. This is, first of all, it's going to be very undergraduate, as you just sort of saw. It's going to be I mean, that is the demonstration of the physics of the guitar, of the wave equation for the one-dimensional spring. So it's not like it's missing anything, but this is going to be a piece, just a little piece of a larger sort of assembled cut, almost comic story for guitar players. And in fact, what I'm imagining is that this whole thing is going to be run at like 5 times speed. So it'll be unintelligible during the actual lesson, but referred to as like, you know, this is what the derivation looks like. And then it'll be like at 5 times speed. And if anybody's particularly interested in it, there'll be a link that you can go and watch the precise lesson itself in a separate normal speed variety. So it's and then surrounding it is going to be some other things in humor, and it's also going to be voiced by a computer. So I have a lot of ambitious creative plans for this, but the idea is it's going to be injected into the community of YouTube guitarists and musicians, because this is an aspect of music theory that's not covered much. I mean, there's plenty of music theory about harmonic analysis and composition and melodic composition, harmonic composition. There's tons of stuff like that, but nobody really digs back into the core level. So I'm going to offer that. That's going to be the plan here. Okay, so let's begin. All right, in this lesson we are going to discuss the physics of a guitar string. And the goal of any physical theory is to calculate how things evolve in time. The idea behind the evolving in time is if we start a system at a certain time, which we will call 0, then that system will move once it's released, and it allows it's frozen at time t equals 0, and then you release it and the thing moves like a spring, or in this case a guitar string. And then at some time in the future, which we will call t, which could be 1 second or 1 millisecond or 1 microsecond, a millionth of a second, we want to know exactly what condition our guitar string is at time t. So the idea is we start with a guitar string at time 0, release it, and then every time after 0, I should be able to tell you exactly what the shape of the guitar string is. So that's our goal. Our goal is to understand why we think we can do this in physics, right? That's our point. So how do we begin this process? It sounds like a very ambitious process. It sounds like something that's really, wouldn't that be amazing? Because when you look at a guitar string, right? When you look at a guitar string, you don't see, let's draw it, right? You see here the nut of the guitar. Whoops, let me do it this way. So now I've paused the video so I can draw the guitar, right? It's a little spontaneous, as you can tell, right? I don't plan these things too much. So let's see, I'll make the guitar string in. Another nice thing that would be nice about Vittle that it doesn't have is the ability to draw straight lines, right? See, so I kind of have to struggle with my artwork with Vittle. I have definitely seen presentation material that doesn't have that problem, right? That's not so bad. Well, that got bad at the end, right? Okay. And then I'll label this thing nut and bridge. And the string after the bridge goes somewhere, right? And then after the nut, it goes to the tuners, right? And then I guess this is the headstock. And this is the neck. And then this is somewhere in here is the guitar body, right? Where does the guitar body usually start? It usually starts around the 3/4 of the way in, right? So we'll put the guitar body. And all right, now that I'm committed to drawing this, I'm sort of stuck, aren't I? And good enough, good enough, good enough, good enough. I guess I need to at least draw this in there, right? And I guess I should erase this. That makes no sense to have that line there. Okay. So for example, take this guitar string here. Here's the guitar, right? There's the body of the guitar, the bridge, here's the nut, and this red line, that's the guitar string. When you pluck that guitar, our goal, what's our goal? Our goal is to understand exactly how this string moves. Now when you pluck this darn thing, it looks like a mess to you. You can't see the thing move. You know it's moving, you know it's vibrating, but at no instant do you have the eyes fast enough to see exactly what shape that string is. As far as you know, the string could be shaped like this, or it could be shaped like this. You have no way of knowing because you just can't see. Its vibrations are so fast, you just can't see. However, it does at every instant have a very precise shape. And the goal of this is to calculate that shape at every time. So we win if we're able to specify any time and any position on the string. So we'll call the position on the string this way. We're going to call that X, right? And then we're going to call the displacement of the string, we're going to call that Y, right? The height of the string. So when the string's sitting still, for every value of X, for every place along the string, Y is always going to equal what we're going to call 0. That's the equilibrium position. After you pick the string and release it, every position on the string is going to have a different value of Y, right? And we want to know every possible value of Y that this string might have. And that's obviously very exaggerated, right? Because the displacements are small. We want to be able to say what Y is at any given time, right? Any given time. That's our goal. And it's an ambitious goal. And we are going to accomplish that by using and applying very straightforward physics. And it's an amazing thing that we can actually do this. So let's begin. All right, so that completes sort of the intro section. I think it kind of motivates what we're doing here. It gets everybody excited, like, oh, can you do that? Can you actually do this amazing thing of capturing like a snapshot of the string in time? So the beginning part is supposed to like, wow, I want to see how you do that, right? Okay. So now I will go to the second part. So let's see. Vinay, thank you. So, all right, so you're recommending GoodNotes 5 is a great alternative. Okay, Vinay, I'm gonna check that out. I am looking for, just because I'm comfortable with this doesn't mean I'm not willing to upgrade. I really would like to get something that can draw straight lines. That'd be awesome. Okay, so now let us begin the actual derivation. Let's see if we can get through this on one take. All right. So the way we start is first we instead of considering the entire string, right? We don't consider the entire string. And first of all, we're going to consider sort of an arbitrary string for now. We're just imagining a string out there and it's got some length, but we're not going to consider the whole length. The way we break this down, the way we come up with this analysis is a process. Philosophically, it's called reductionism, right? We are not going to look at the whole string. We're going to just look at one little piece of it. We're going to look at that little tiny piece of string. In fact, ultimately, the piece of string we're going to look at is so small that it's literally infinitesimally small, right? And that's where calculus comes in. Calculus allows us to take a small piece of string and then just push it to be infinitely small. But we're going to study just the motion of this tiny piece of string right here. And from that little analysis, we're going to be able to understand the entire string. So that's our goal. So let's blow up just this little piece of string. All All right, there it is. That's the little tiny piece that is just, it could be anywhere along the length of the string, doesn't matter. We're just looking at what's true for this piece is going to ultimately be true for every piece. So now, when we study this little piece of string, we are going to apply Newton's laws. Newton's laws. And Newton's laws, they govern almost all physics that we experience in the world. They're governed by Newton's 3 laws. And we're going to apply them to this piece of string. So the first thing is, let's understand and orient this piece of string, right? So we're going to just say that the left side of this piece of string is located at a position X from the nut. So the nut is this way, right? And the bridge is this way. And we're going to say that X is somewhere between the nut and the bridge. So X is somewhere between 0 and 25.5 inches if you have a Stratocaster style guitar. So that's the left side of the piece of string. The right side of the piece of string, this part, is going to be located at another position that's kind of close to X, because remember, it's a small piece of string. So the position of that is X, and it's plus some little bit. And that little bit we represent by this symbol delta X. So delta X is the little bit on the right side, right? And now we know where the left and the right side of this little piece of string is. Now, what else characterizes this string? Well, the string is sitting there in space at this angle, right? And the angle on the left side, right? I'll put this angle in blue. This angle on this side is theta. We're going to call that angle theta. And theta is not the same on the left side as it is on it's not the same on the left and on the right. In fact, everywhere along here, theta is slightly different, right? Because the string is bending, right? The whole point of this is the string bends. If theta was the same everywhere, then the string would either be in a straight line or it would be totally flat, the total overall string. So the theta is clearly changing. So over here, theta is slightly different. So how do we express that? Well, we say that theta has a value at the position X, and here we say theta has a value at the position X plus delta X. Right? So now theta has 2 separate values. So that's an important thing of characterizing the string. The other important part of characterizing the string is it has to have mass. It has weight, right? So the string having weight is captured by, well, let's just say this little segment of string has a certain mass, and we'll call it M. Now, the problem is that we're looking only at a tiny little piece of the string, right? So the overall weight of the entire string from 0 to 25.5 is some total mass M, right? And the length of the string is 25.5 inches. So the mass per unit length is this ratio. And every string has a mass per unit length, right? If you go to any string manufacturer and you can look up the mass per unit length of all of their strings. So for example, let me just point out a typical, well, let's not worry about it right now actually, but the mass per unit length we're going to write down as the Greek letter mu, right? And the total mass of the string is the mass per unit length times this length of the string. Now one of the issues here is, what is the length of this little segment of string? Because it's not, by the way this picture looks, it's not just delta x, right? It's not just this bit. You know, x plus delta x gives you this distance here. In fact, I could even write that down, right? This distance here is delta x. But we are going to later make an assumption that this is a very small angle, right? That the string doesn't really bend too aggressively. It's a very small angle here. So we can assume that the mass actually is x, the mass density times this little length, delta x. And that's going to be the mass of the string. Okay, I've paused it, so I think everything's going well so far. It's kind of interesting because the irony here is none of the guitarists that watch this is going to understand any of this, right? This is already kind of nuts to them, right? And so I'm kind of speaking in between the level of somebody who's completely ignorant of partial differential equations and somebody who knows it well enough that this is all like super easy. But I have a solution for that in the final mix, right? This is more of a performance piece than it is an actual edifying piece of study. Welcome, AA. What a great name, AA. Does that mean anything? Linear type. Hello, Mr. Lily. Lily. Well, that's an interesting way of saying it. I've always gone with Xylix. I don't, if in case that matters to you, Xylix is sort of the way I've always said it. Okay, so now we will proceed with the taping here. So what I typically can do is I can stop the recording and I can view what I've done so far, and I can actually play it back. So for example, I can play back just the last, see, I can record in scenes, right? This is why Vinay, this is so good, right? Is this thing is playing back, although I gotta say I'm not hearing myself. Why am I not hearing anything? This thing better be recording. Hold on. Let's see. Huh, it's interesting. Oh, I see. Yeah, okay. So what's happening is when I put this through to the stream, the sound is routed to the computer. So it's a different. So I can't just hear what I've said. That's actually a bit of a problem. And I don't want the microphone to capture it. I guess I better put on headphones and see if I can hear it that way. I'm curious to see what actually makes it to the stream itself. All right, I got to reroute my headphone wire here. I'm trying to listen to see what it sounds like on the stream, but I got this 30-second delay issue going. Well, you know what? I'm not going to worry too much about it. I'm just going to keep going. All right, so now let's see. All right, so I've checked that out. So I'm going to begin. So we've got as far as the mass. So let's continue. All right, so now we know almost everything we need to know. One thing I didn't mention is this diameter. Like the string has a certain amount of width. And this is important because the wider it is, the more the string is going to resist being bent, right? The string is bent here a little bit, so you can say, it's not going to resist much. But if you know that if you tried to bend the string more, it would kind of fight back. It would be a bit springy, right? And we know that guitar strings actually are a bit springy, right? They're not like literal pieces of string, which are completely you know, a literal piece of string you could just sort of wrap around like this and it'll just sit there. A guitar string won't do that. A guitar string will tend to straighten itself out if you allow it to. As soon as you unpack it from the kit, it straightens itself out. That resistance to bending is an important physical effect that we will be ignoring, right? Very important to understand. We are going to ignore the fact that the string itself wants to straighten out. the only force that is going to be acting on this string is the tension. And when you have a perfect string like this, tension can only operate in a direction tangent to the ends, right? So tension has to go in these two directions. The tension can only pull directly through the core of the string. It'll never tend to want to bend the string back. There'll never be a force like that on our ideal string. So we have basically what's called an ideal string. And that is an approximation, my friends. That is an important approximation. It's legitimate, but it's important to understand, because eventually we'll talk about removing that restriction, not in this lesson, but some other lesson. So with that in mind, now we know the direction of the tension is always in the same direction as the string itself is actually facing, right? It's tangent to the shape of the string. So it's going off in this angle, basically. Whatever this angle is, the tension's going off in the same angle. And so I think this is it, right? This is a complete description of one tiny little bit of the string. Now, what's missing, of course, is, obviously this string, this isn't cut away. The real string is actually there, right? The rest of the string, is there, and it has its shape, and this is exaggerated, but the rest of the string is there. We're only looking at a little piece of it. And the piece that we're looking at, right, this little piece right here, when we cut a piece out like this, a piece of matter out of some other piece of matter, what we're creating is something called a free body diagram. So I can pause the video and write this so it looks like it appears right on the screen, right? And a free body diagram just focuses our attention on just what's inside this red line. And this force, this tension force, is the connection between the edge of this free body diagram and the rest of the material of the string. And we know that that's the only place forces can exert themselves, with the possible exception of gravity, right? This string has a weight, so presumably there's a force going down, and that's the force of gravity, right? And that gravity is going to be that force is going to be the mass of the string times the acceleration of gravity, which would be mu delta x times g, right? And ultimately, that's something we have to decide. Do we want to consider that or not? Now, in the end, we're making sure that delta x is extremely small, right? And if delta x gets small towards zero, then this force of gravity is going to become zero. But the tension never changes. No matter how small we make this piece of string, the tension on both sides is going to be constant. And that's a factor of being a string, is the tension is constant throughout the entire string. If it wasn't, right, if the tension over here was different than the tension over here, the string would have the possibility of accelerating to the left or the right. But our string only moves up and down, right? Up and down. So ultimately, this gravity effect is negligible, and we will ignore it. We will ignore gravity, right? So I'm going to get rid of the gravity. Okay, I think I'll get rid of the free body diagram too, because that was just to illustrate the idea that we're not cutting the string. Okay. And let's see, I will now select, let's select everything and sort of shrink it down and move it over there. Hold on. All right, so now we have everything set up. The setup is good. We've drawn our little piece of string. I'm going to move this setup over here so we can always reference it, right? And now we are going to actually engage Newton's laws here. We're going to basically say a few things. The first thing we're going to say is that the string is not moving left or right. That's an assumption. We should track our assumptions. So let's see, the first assumption we've already mentioned was that theta x. These angles are going to be small. They're going to be small. Now, in science, we're not allowed to say small and big and giant and huge. We have to do everything relative to something. So when I write theta is small, I have to put small in scare quotes until I can quantify exactly what I mean by small. We have to be very, very precise by the meaning of the word small. So let's push on a little bit and let's look for that first place where I can say what small actually means. So applying Newton's laws to the tension, right? We're going to look at the tension. On the left side over here, the tension has two components. One is pulling the left side horizontally. Well, not even just the left side, it's pulling the whole little thing horizontally, and the part of it is pulling it down vertically. So let's look at the part that's pulling it horizontally. I can write that the tension times the cosine of the angle theta of x, right? That is the amount of tension that is pulling the string down, right? So since it's going, is it going? No, horizontally. So it's to the left. So the tension that way is negative, right? It's because we're going to say that x gets positive in this direction, right? That's x positive this way. So the horizontal on the left side of the string is minus t cosine theta. On the right side of the string here, it's plus the tension times the cosine, but the angle's different, right? Cosine, it's not theta of x, it's theta of x plus delta x, and that angle might be different, right? The angle over here is not going to be the same as the angle over here. So this is not going to cancel to 0. So what it'll actually be is it'll be, when we add these together, we do want the whole thing to equal 0 though, right? Because we are making the assumption that the particles don't move left and right. So this the tension on this piece of string must balance, right? So that's an assumption, right? Well, that's what we're after. So let's see how this is going to work, right? So t, I think I can switch the two cosines. Cosine theta of x plus delta x minus cosine of theta of x, right? That's got to equal, let's see, do I have on my, I think I need a parenthesis there, equals 0. But now I've said that theta is small. And what's interesting and what's important is that the cosine of theta, when theta is small, is always equal to 1. If theta is small, the cosine of theta equals 1. That's, of course, because the cosine curve at 0, let's see, I make a little cosine curve right here, it's flat up there. You're at a an extremum of the function. And so if theta is small, cosine theta is equal to 1, which is great because that means this equals 1 and this equals 1, and then you end up with t times 1 minus 1, which equals t times 0, which equals 0, right? And that's good. The horizontal force is balanced to 0. But this is where we now can understand what theta is small means. Theta is small means that this approximation is good enough for us. It's valid. It's not exact, right? I mean, the cosine of a very small number can be calculated, but we're going to say that it's so small that whatever we're doing, we're just going to presume it's 1 because it's so darn close to 1 that it's good enough. That's what small literally means. It's this mathematical relationship that establishes small. Okay, so we've taken care of the horizontal forces, and that has allowed us to assert the nature of small, right? Okay. All right, so now I'm pausing the video, and I'm going to erase. Wait a minute, let's see, undo. Let me, instead of erasing that calculation, let me go to a new screen. I'm going to paste this little piece on. Let's go up here and find a spot. And let's see. All right, so now I've got a spot. And let's now talk about the vertical forces. So I'm going to begin playback again. All right, so with this part done, we are now going to study the vertical forces. The vertical forces on the piece of string, very similar calculation, right? We're going to say that on the left side here, on the left side, oops, I want to point on the left side. We're going to calculate the vertical forces, and we're going to write T. It's going down, so it's going to be minus T times the sine of theta of x, right? And from that, we're going to add on the right-hand side. So this expression is the vertical force on the left side, and it's going down, right? And on the right side, it's going up, so we're going to add it, and it's going to be the sine of theta of x plus delta x, right? Now, these two don't cancel necessarily. They actually equal something. And what do they equal? They equal the mass of the spring, which is this mass density times delta x, right, times the acceleration, right, the acceleration. And the acceleration is what we're calling this vertical movement here, right? That vertical movement, that is what y is. I said we're calling it y, so I better write it down. Y is this vertical displacement. So this is going to equal the acceleration. And the way we write that is it is the second derivative of y with respect to time. Right? That's what acceleration is. And now we apply our smallness again, right? What happens? We know theta is small. So what happens to sine when theta is small? Well, the definition of theta being small relative to sine is that sine of theta equals theta. A really critical and very strong relationship. And this, of course, is because the sine curve right here near 0 basically looks like a line. That basically looks like a straight line. And you have to be in that regime for the wave equation to be truly ideal. So small it's basically small angles, which ultimately means y is always small. And when I say y is always small, it's always small relative to the length of the string, right? Because you got to specify. If I'm saying y is small now, I have to say, well, what is that small relative to? That means y divided by L is much, much less than 1, right? That's what small there means. Okay, so now that we have this expression, we will now simplify these signs, right? I can now erase them because we have our approximation, and I can say that equals the value of theta. You know, I better not put parentheses there because I don't want anybody to think it's some kind of function. So that's theta. And this one was theta plus, I'm sorry. This is theta at x, and this is theta at x plus delta x, right? That's both applying this. So that's sine theta equals theta and sine, let's see, how do I do it? I want to do sine theta at x plus delta x equals theta at x plus delta x, where this one is sine theta at x equals sine theta at x. Okay, so then of course this comes out and we end up with t. Let's go back to black here. We end up with t times theta at x plus delta x minus theta at x. And that has to equal the mass times the acceleration, right? So that is the governing expression from Newton's law. And the Newton's law we're applying is that force equals mass times acceleration. And here acceleration is y double dot. So this is actually getting to be pretty easy. The next step, the insightful next step that's really important to see, is that this angle, right, this angle theta of x, that's the slope, right? That is the slope of this piece of string at the end, right? And the reason that that's the case is because when theta is small, we also have another assumption that the tangent of theta equals theta, right? And so I can replace this with the tangent of theta of x plus delta x, and the tangent, I can put little tangents in there. But those tangents we know are actually equal to the derivative of this function that we're seeking, because we're seeking a function y, which is the height, as a function of x, right? And a function of time. Remember, I tell you the time, I tell you the position, and you report back to me the displacement y. That's what our goal is, right? So this, I can now write this as the tension T times the oops, I didn't write this correctly. I forgot the other tangent, right? Times the tangent of theta of x. And notice I'm flipping things in order to get rid of these minus signs that are in front. But the tangent of this angle is equal to the first derivative of x, right? That's what the tangent of that angle is by definition. So this is equal to t times y y dot at at x plus delta x minus y dot at x, right? And that equals the mass density times delta x times, oops, let me erase this, times y second derivative, right? And now if I divide everything through by delta x, the delta x cancels over there, and I put the delta x down here, and this guy is the definition of the derivative, right? The derivative of y dot. So now I'm going to get t, whoops, you know what? This y dot is, that's bad news, right? Oh, that's a mistake, right? Y dot represents the derivative with respect to time, right? So we need some symbol to represent the derivative with respect to x, right? So I'm going to make it y prime, right? So this now becomes t y double prime, right? Because this is the derivative with respect to x again, right? So we get t y double prime equals mu y double dot, right? So if we write this out fully, we end up with, I'll write this out without I get d squared y dx squared equals mu d squared y dt squared, right? And the final form of that is, I erase this, and this, I think the final form that was usually used, I think they keep the t, they divide by mu like that, and that's it. That's the final wave equation. It's often written in a slightly different form. It's often written as, usually with the time on the left, so it'd be dy dt squared equals, and then we define a number c, which is the square root of time over the mass density. And then we write c squared d squared y dx squared. And that is the governing partial, well, shoot, another problem here. Okay, so as you can see, I'm now speaking to the stream. I've gone off the rails here, right? you always have to decide how much is too much of a mistake, right? How much is does it do you need to go back and redo it? So a couple things that I read, obviously messing up with the prime, that wasn't so bad. That's kind of one of those mistakes that somebody who's watching it sees it probably, and when you catch it, they feel like they're smart, and that's good. So that's good to have a mistake like that. The problem is down here where I talk about the second derivative, I'm using ordinary derivatives here, right? And those should be partial derivatives, right? And now it's getting to be a little bit too much, I think. I think that's an error that I should have, the equation is just wrong, right? It's just not the way it's supposed to be. So the spontaneity is not worth the level of confusion that might be introduced there. So I am going to back up and begin this section again. Let's see. So to do this, to back this up, let me first figure out where I would have to go back to. Fortunately, I can do this in Vittle because it's I can construct this out of scene segments, and that's really, really convenient. So I can play back this segment. Okay, all right. So I'm going to get rid of that scene. So I'm now eliminating like the last 3 minutes of my work. I'm just deleting, and I'm going to redo it. Let's see how that goes. So where did the last 3 minutes started? Right here. So I need to erase just about everything. And I'll erase all of this. And I'll erase this. And I'll erase this. So we come back up to here. And I'll erase this stuff here. Okay, so now I'm ready to begin again. So understanding these things, I say now, understanding the small angles that we're dealing with, and understanding that tan theta is also approximately equal to theta, I can now make this expression look like this. I'm literally replacing those angles with their tangents. But the tangents are the first derivatives of the function y. So we know that the function y, this is the guy we're after, right? Y is a function of x and a function of time. That's the whole point here. And the derivative of y with respect to x, which is given as the partial derivative of y with respect to x, is going to equal these tangents, right? So I can now rewrite this as t is the partial derivative of y with respect to x evaluated at x plus delta x, and this one is the partial derivative, that's minus the partial derivative of y with respect to x evaluated at x, and that equals mu delta x times the partial derivative of the second partial derivative of y with respect to time, right? So since we know that our displacement is is a function of x and a function of time, I now know that this vertical acceleration is its partial derivative with respect to time, and these tangents, the tangent is the slope, right? The slope that's what the definition is of a derivative, but those slopes are going to be precisely these first derivatives at x plus delta x and at x. So now we're very close to done. We have one step left. We have to divide through by the little bit of string, right? This little bit of delta x. We decide to cut this string into a small part. We're going to divide through by that delta x, right? Divide through. I'll put that delta x under here, under the left-hand side. And now's where I want to say now's where the calculus comes in, but obviously the calculus already exists here and here. But this is the literal definition of the derivative once I decide to make my string length infinitesimally small. So right when I said earlier, we're going to take this string length to be infinitesimally small, this is where we do it. Here we're going to take the limit as delta x goes to 0, right? Now that limit does not affect the right side, right? That's constant. There's no delta x over here, but there is delta x over here, and this is the definition of the derivative, of a derivative of partial y partial x, and that means that this side is going to become the tension times the second partial of y partial x, and that's what that limiting effect does, and we get the mass density times the second partial of y with respect to t, and then we are basically done. We'll put this in the form that we like. Usually time is on the left. This is the form I like. dy dt squared equals t over mu times partial squared y partial x squared. And that is the partial differential equation that describes how our string moves in time. And the answer to this partial differential equation is a function y, x, and t. You give me the position on the string and some time after you pluck it, and you take those, you plug them in here, and out gives you the vertical position of that spot on the string at any time, and it can be positive or negative. It'll oscillate, and 0 is usually set to be the equilibrium position. So there you have it. Solving this partial differential equation means knowing exactly how your string moves, and we'll talk about solving it in another lesson. Okay, I think that's it. That's not so bad. That'll serve my purpose. Let's see how long this thing was. Let's catch back up with the chat. Tan theta to the derivative of y is the most confusing. You know, that's a really good point. That's a pretty good point. Hide the key. There's a lot there. I mean, if you don't know calculus, none of what I said is going to make any sense, right? But if you do know calculus, I think understanding that tan theta is the derivative, usually that's how the derivative is introduced, even in pre-calculus. So, you know, the problem is the real weakness of what I just did is the obvious fact that the introduction was almost like physics for poets, right? And then after that, it's like, okay, all you guys who just finished calculus, you know, let's talk about partial differential equations, right? So it's incongruous, right? The audience is completely incongruous, and I mean, the materials is sort of incongruous for the audience. The way I'm going to use this is going to be presented at like really fast speed. It's going to be part of sort of a comic presentation for guitar players. I think I'll be able to get away with it. Like I said, it's I haven't done this yet. I haven't done the whole thing before, so we'll see. But I am going to go through a whole nother one in a minute that solves the partial differential equation, for the actual guitar string, right? I'm going to literally do it for a guitar string. Let's see. Can you dig it? Please make a video on solving the Einstein field equations. I wish I could. Can you dig it? I wish I could. We did do the Schrodinger equation at the end of What is GR? Did you see that? Can you dig it? Did you see the last 2 or 3 lectures in What is General Relativity? We solved the Einstein field equation for the spherically symmetric case. That's strict. I gotta say, I've done a work with a lot of different spacetimes, but that's, I think, the only case where I literally solved the Einstein equation straight up. Maybe we did it. Maybe we did it for the charged black hole. I can't remember if we solved the Einstein equation just straight up for a charged black hole. Yeah. Have a look. The last few. The What is a General Relativity section is over, and the climax was solving the Einstein equation for the spherically symmetric case, and it was fun. Which number? I think it's like 73, 74, or maybe 72, 73, and 74. It's the last ones. That's sort of where we ended it. But I don't think a straightforward analytic solution for the Einstein equation, I think that's as far as I was willing to go. Now, the good news, though, is that we have a lot of metrics for spacetimes, and the obviously interesting one next would be the Kerr spacetime, the rotating black hole. And from there, that would be the case where we start from the metric and we proceed to find the geodesics. However, I've got to remember how you show that metric actually is a solution to how you show that metric is actually a solution to the Einstein equation. I know that it was very difficult to find, and I'm trying to remember exactly how they did the demonstration that the metric solved it. I mean, I'm sure at some point somebody literally took the metric, found the connection, took all the derivatives of the connection, found the curvature, found the curvature tensor, then found the Ricci tensor, then found the Ricci scalar, subtracted everything, found it to be 0, because it's still Ricci flat, right? The Kerr black hole, at least it's Ricci flat. It's axially symmetric, but it's still going to be Ricci flat. So you can definitely go through all of this and show that RAB equals 0, but so that's something we could do. I'll go back and look into that. That might be a good topical subject, actually. I've always wondered, how do we know time is actually dimension? One of your early videos, you talk about how you need to think of time as an actual dimension. You never explained why. Well, can you dig it? That's not even a general relativity topic, right? That has nothing to do with, well, I guess you said also, so it's a special relativity topic. You just got to look at special relativity very carefully, and it's very evident right away, right? That that time, well, I guess just the Minkowski spacetime. Minkowski himself was the one who kind of figured out that we have to understand time as part of the geometry of spacetime. And the fact that you have this Lorentz geometry, the only meaningful distance between 2 points, right? The only way to calculate an invariant distance, a distance that all people, all observers, no matter what their relative state of motion, a distance between 2 points in space-time that everyone can agree upon, requires that you know where the point is in space and when the point occurs in time. If you don't know those 4 things, you cannot calculate a meaningful separation between 2 points. It just isn't, because everybody will have their own measurement. But so you must introduce time. So the location of every single thing has to be x in space, y in space, z in space, and t in time. And if you don't do that, you can't do meaningful physics, because there's time dilation and spatial, what is it? Not space dilation, it's space Lorentz contraction of distances, right? And so everybody will measure a different distance. So if you try to build physics based on just space, then it will be different for every person or every scientist moving relative to every other scientist, and it would be an impossible task. But when you include time, it works out, because special relativity is true, right? It wasn't obvious that it worked out, but once you realize that you need those 4 things, then time's just obviously a dimension. The geometric distance between things involves time, which now suddenly makes time like a dimension. The thing that makes time special is that time stays special, and the reason it's special is because when you calculate that distance, the time difference between 2 things shows up with a negative sign. And that negative sign is critical, because that's what establishes the Lorentz geometry of space-time. But that's, in a nutshell, the answer to your question, why it has to be an actual dimension. Now, I guess the word you're using here is actual dimension. So I'm not quite sure, can you dig it? If you're thinking an actual dimension as like literally another spatial dimension, that's kind of tough, right? Now there's a certain philosophical edge to this. It's certainly a mathematical dimension, right? So we can draw it as though it's a spatial dimension. If we suppress a spatial dimension and replace that suppressed spatial dimension with time, then you will get a 4-dimensional structure, or you will get a 3-dimensional structure that will actually look like 3 spatial dimensions, but one of them is time. You just have to remember that if you calculate distances in those 3 spatial dimensions, you're going to get it wrong if you think of time as a regular distance, because it isn't. It's got this negative sign in the Lorentz signature. But my point is that so on the other hand, so it's not an actual dimension like a literal spatial dimension going off in a direction we can't see. That's probably not a useful way of thinking of it. On the other hand, before I go too far down that road, once you study the way the metric changes as you cross the event horizon of a black hole, the time dimension does become a space dimension, mathematically speaking. Obviously, no one's gone through a black hole to check all this. And there is a theory that says, yeah, you can't cross the event horizon. You get cooked. You get cooked. So, but if you just look at, any elementary textbook talking about black holes, you'll see very clearly that the light cone turns over on its side, and you now have what was a spatial dimension assumes the role of a time dimension, and time dimension assumes the role of a space. So it is interesting that there is this essence in the math of it being an actual dimension, because it can be interchanged at this event horizon of a black hole. So, I guess I shouldn't be too firm about, don't think of it as a literal space dimension. I mean, in some sense, maybe, yeah, that's not a bad idea. It's sort of immaterial, because this is all about modeling reality, right? It doesn't have to actually be. And as soon as you start talking about actually being, you do get into the philosophy of the sort of a metaphysical philosophy and a epistemological philosophy, and things that are a lot more complicated. Okay, so anyway, so back to this. So this is complete. Now I want to do one where I actually solve the wave equation. That one's going to be a little bit longer. So we'll just do probably a separation of variables here. Something I didn't do here is I didn't take t over mu, throw a square root on it, and call it c squared, sort of the speed of sound squared thing. I didn't do that, but that's fine. That's not going to be too important. that's not relevant for what I'm after here. If this was a real true deep detailed lesson on this would have gone on a lot longer and been a lot more careful. It would have been immediately non-dimensionalized, as somebody suggested earlier. But now I think we do want to derive the actual solutions of the one-dimensional wave equation for fixed boundary conditions and a plucked guitar string, which would be sort of an asymmetric triangle. I think I've chosen 7/8 of the way down these away from the nut, 7/8 of the length away from the nut, with a 1 millimeter displacement, and actually calculate the harmonic spectrum of that. I think that'd be cool. And so I'll do that in a few minutes. I'm going to take a quick break here. Now, if my stream was really squared away, I'd have a screen that comes up that says break. Let me see if, oh, here's what I can do. Watch this. See how clever I am? I will do this. I will write, let's see, I'll take my thickness up. Okay. And I will write, that's a little too much. BREA break for 5 minutes. All right, maybe I'll put a little heart on it, just so everybody, all my viewers know that I love you all very much. All right, I don't think I need to record that. Let me see if that pops up correctly. Wait a minute, why is it, what's happening here? That's weird. Why is this not showing up at all? Did I lose my, oh, I lost my screen mirroring. That's strange. I wonder, that was weird. I lost my screen mirroring. Yeah, see, I'm still kind of getting this all down. Let's see. Let's see if this gets up there the way it's supposed to. Yeah, see now. All right. So now I think it's time to yeah, there's definitely bugs I'm still working out of this thing. There's no doubt about that. Um, but we will. I'm still, for example, trying to fit this thing to the screen correctly. But okay, so now what I'll do is I'll do a second little video demonstration. And this second video demonstration will be just the solution of the wave equation. Now, what's interesting is a couple of the assumptions I didn't mention there was some that I consider pretty important, in particular damping. Damping is actually, I think, one of the more interesting elements of the elementary wave equation. A lot of people don't know that the damped wave equation, so let me just write that down here, right? The damped wave equation, let's see, where am I going to put it? Goes like this. It would look like, whoops, now I've made my thing all big, huh? Let's go back to normal thickness, maybe even a little smaller than normal. So the damped wave equation is the mass density times, let's say, the way I was doing it before is the second partial, let's use u, right? So now the solution is u of x and t, right? The second partial du dt. The normal wave equation now is t second partial u dx squared, right? And the damped wave equation adds a term gamma partial u partial t. So it's a velocity dependent, the vertical velocity of this string, the vertical velocity of the string, will execute a damping. So it's sort of like the string is in some kind of viscous medium. So as the string goes up and down, the medium tends to resist its motion. And what most people, I don't know, what many people don't know is that this equation is fully separable. This equation is separable just like the wave equation is. So if we were to execute a separations of variables demonstration, we might as well do it on the full damping equation, right? It doesn't, normally, of course, if you derive the wave equation, you solve the wave equation, and then you complicate it by damping, and then you compare the damped solutions to the undamped solutions. The alternative is to just solve the damped version and then set gamma equal to 0 and show how that is the undamped version. So I think it's my preference to go ahead and just quickly introduce the damped version and solve that. I think that sounds like fun. So let's see. So how will I proceed? So I'm going to just do a little bit of a warm-up here. I think the first thing I'm going to do is clean up the notation. So we're going to go with mu u tt equals tension uxx minus gamma ut, right? And then let's see, then I'm going to say, all right, let's deal with the issues of dimensionalization, right? So how would we do this? We would, let's see, I guess what we would do is, you know, it's an interesting point, because you can, you can choose your dimensions of gamma in two different ways, right? If you leave it like, if you do it this way, then you can end up with UTT equals T over mu UXX minus gamma over mu UT, right? And then the next step typically is to define C equals the square root of T over mu. And then you write UTT equals C squared UXX minus, and now you have some constant that you're calling gamma over mu UT, right? And so this has to end up being in units of acceleration. Alternatively, we could have started with, when I was up here, right? When I was up here in the beginning, and I just added this term, obviously the gamma of this term, the units of that gamma are dependent on the units of mu and tau. But had I, before I put this term on, if I didn't put that term on, and then I divided through by mu here, and then I got rid of this and called it C squared, and then I said, oh, and by the way, we're going to take this subtractive term and put it on. Now gamma has different units at this point, right? And that's what this reflects. So I could actually just then, just change that and call it some new unit thing, call it, alpha, right? And that would be the units of the damping. I wonder what the actual, I don't know if I feel like going through and figuring out the distinction between those two unit systems, but I have to decide what formula I want to start with. And let's see, the last time we ended with this formula, so I think we begin with this formula, right? Okay, so that'll be fine. So we'll start with UTT equals C squared UXX minus, and we'll call it gamma. I like gamma U of T. And then we'll just do the basic substitution where we say U x of T is X as a function of X times T is a function of T. So we'll just do the obvious separation. God, it's been so long since I've done this, but we will plug on. So let's see, the second derivative of this thing with respect to T is T, I'll call it TTT of T. And I guess by the product rule, it's that times X. Obviously I don't need the, it's obvious that the function capital T is only a function of T and X is only a function of X. So I do this, and then I'll say C squared, and then UX, the second derivative with respect to X is going to be the opposite. It's going to be T, and then it's going to be XX, like that. And then the first derivative with respect to T, so it's going to be minus gamma, let me erase this, minus gamma X T T, right? Yeah. So now I think the obvious thing is you divide by X, right? So I get T equals C squared T XX over X minus gamma T. And then divide by T, right? You get T divided by T equals C squared XX over X minus gamma T over T. Okay, and this is where everything separates, so we end up with T over T minus gamma T over T equals C squared X. Am I missing a derivative on X? Yeah, XX over X. And that has to equal some sort of separation constant. Now the separation constant, I do remember, is frequently chosen to be minus lambda squared. So we're forcing it to be negative, right? So I think that becomes helpful. When does that become helpful? It becomes helpful because we want I think it just makes the form of the resulting differential equations just a little more obvious. There's one less negative sign to deal with. I think that's the way it goes. So let's see. Hold on. Yeah, I think that's what's going on. Okay, so regardless, then how do we punch this out? Then I think we're going to say c squared xxx plus lambda squared x equals 0, right? And then we're going to say, I guess the t's, we get t minus gamma t plus lambda squared t equals 0, right? Is that how that works? Why do I have a minus gamma there? Yeah, that should have been a plus, right? It should have been a plus because this coming over to this side is a plus sign. So that should have been a plus. Yes, that's good. I think that's why we choose the minus lambda squared. Is so this is like a second order ordinary differential equation for t with plus signs, makes it easy to solve. And then this is a second order ordinary differential equation for x with that plus sign, so it's easy to solve. So I think, so this guy you divide through by c squared, right? So we divide through by c squared. So we have lambda squared over c squared. And the solutions here are x equals a sine, I think it's lambda over c, right? Which is why the square is there, right? That's why the square is there. So it's when you get the sign, you don't have a square inside the sign, and that is the function is the dependent variable is x, and then it's plus b cosine lambda over c x, right? So that's the first one. And then the second one, the characteristic equation, right? R squared plus gamma r plus lambda squared equals 0, right? And boy, can I remember the quadratic minus, let's see. I know this is a far cry from differential geometry, but let's see. Let me see if I can get this right. So it's minus gamma over 2 plus or minus the square root of gamma squared minus 4ac. So I guess that's 4 lambda squared it's also an over 2a, so there's going to be a 2 here. What is it's 4ac. Did I mess up with my t here? Hold on, let me see. What have I got here? I've got lambda over c. You know, I think this isn't the form that I'm after. That's why I'm doing this dry run, right? The form that I'd rather have, first of all, I feel like I'm missing a right? This C squared appears here, right? And that's going to stick with, so when I subtract t, that c star is going to stick with the x. But I could just as easily take that c squared and divide here. But no, I don't think that's going to be what I want. So I think I'm just going to want 4ac like this. So I'm going to use my 4 right there, 4 lambda squared over 2. Okay, and all right, so that would give us our so now the point is that with the damped equation, you have the possibility that the coefficient r is completely real, and in that case you will have this damped solution, right? That's the point. Okay, so I think that's, the screen is too, oh yeah, look, see, that is really weird. Thank you for saying that. The it is interesting how sometimes the transform of this presentation just suddenly goes nuts and changes. I think, you know, the software that I'm using to stream is called Streamlabs, and it's a bit it's not totally stable with all of its sources. I've noticed if I'm using, I think it's not very good with handling multiple screens. So if I tell Streamlabs to stream a certain window, which is what I'm doing now, I'm having it stream the window of the software that's reflecting my iPad onto the computer. If I move that window around, it'll suddenly resize it. So for example, I'm going to grab the window on one of my monitors, and I just moved it by, I don't know, a few inches, and it seems to be okay, but as long as I keep it on that one monitor. But even there, you notice it jumped a little bit, and it shouldn't have. But if I switch it, now I'm going to switch it to another monitor. Now suddenly it changes in size, right? It's not able to compensate for the fact that the monitor is different, and now it reformats itself. So there's these idiosyncrasies in the Streamlabs software that I'm just getting used to. All of these streams right now are sort of test streams. But anyway, okay, so that is going to ultimately be my my method of solving this for the my method of solving this for the damped wave equation. Although, you know, you could argue that heck, since I didn't do damping before, why am I doing damping now, right? That makes no sense. So maybe what I do is I don't bother with the damping, and we just stick to the straight up wave equation. That's hard enough as it is, especially with the initial condition. And all I want to do is blast through it. It's not like I want to it's not like I want to do some detailed analysis. I just need a presentation. So I think what I'll do is yeah, I think I'll get rid of this, and instead of the damped equation, we'll just stick with the regular solution of the wave equation. Then we'll talk about damping some other time. So yeah, okay, so let's go ahead and do a recording of it. Let's just begin. I want to thicken my lines. I don't like the, I think a line thickness of 2 is better. I'm going to stick with that. All right, so let's give this thing a title. solving the ideal string wave equation. And I will write partial derivative u squared partial t squared equals, and I'll write t over mu partial u squared partial x squared. Okay, so now, now that we have derived the ideal string wave equation, we are going to solve it. So what we mean by ideal string is that the tension along the string is entirely constant. We also had the assumption that the angles were small, which can all be traced to the idea that the displacement of the string from equilibrium, right? Here's the string, here's equilibrium. This distance here, which is u, right? That distance is what we're calling u for this version of the equation, right? So the solution of this is a function of x along the string. We're at the nut, x equals 0, and at the bridge, x equals 25.5 inches for the Stratocaster model guitar. U is this displacement right here, this displacement above the resting position of the string. And as we are suspecting, the string is actually going to have some sort of complicated shape. And our goal is to find that exact shape, which is tantamount to finding this function u. And we know that this function u is completely defined by this differential equation. And when I say completely defined by it, I have to be careful, because not only do I can solve for the function u from this partial differential equation, but strictly speaking, it is not completely defined just by the equation. I also need to know some facts about u. For example, I need to know the boundary conditions of u. What is u like at the two ends of the string? And I also need to know is what condition did the string start in, right, in order to, before we let it go, right? What was the initial condition? So I need boundary conditions, which we sometimes call BCs, and I need an initial condition, which we call the IC. And then with those boundary conditions and the initial condition, then the problem is completely well defined, and there's a one solution for u. And now we're going to hunt that solution down. All right, so now I'm pausing it, and I will erase a bunch of stuff. I think I'll just go to a new screen. Okay, see, this is really weird. I went to a new screen, but what's streaming is not the new screen at all. It's like my mirroring stopped as soon as I went to a new screen. That doesn't make much sense, right? I wonder if that happened in the last lesson. If you guys saw, if as I was talking, you just saw nothing change, right? Let me know if that's happened, if you happen to be here when that happened. If nothing changed while I was streaming the last part of this, but now I just noticed that the mirroring of the screen seems to abort when I change the page. Okay, so anyway, let me restart this here. So I need to rewrite this. All right, so this is the equation we're working on, and what we'll do is we will solve it in generality and then apply these boundary conditions and initial conditions at the end. Usually when you deal with this, you assert the whole problem. You assert the equation you're solving, which is the partial differential equation of the wave equation. You assert the boundary conditions, you assert the initial condition, and then you proceed to solve. So we're going to assert these a little bit later instead of at the beginning. We're also going to clean this up a little bit with a different notation. We're going to say the second derivative of u with respect to time is u sub tt. And we're going to say the second derivative of u with respect to the length along the string is uxx. And, oops, that's not a square root there. I'm going to introduce the number c, which is the square root of t over mu, and I'm going to put c squared right there, right? And that just makes things a little bit simpler to deal with down the road. Frequently when you learn and you watch people solve differential equations or you read books about it, you see these weird constants coming in sort of arbitrarily almost, and it turns out they're designed to be convenient later. So be it. All right, I'm paused again here, thinking about the next step. So I'm going to write in red. The method we are going to use to solve this equation is called the method of separation of variables. It is absolutely one of the most critical mathematical techniques you need to know, and it's usually demonstrated on the wave equation, but also on the heat equation, but we're going to do it today for the wave equation. And the crux of this technique is to make an assumption about u. U is the function we're after, right? It's a function of x and a function of time. So if I know how long it's been since you plucked the string, I can tell you for any position on the string, its displacement. And I can tell you the exact shape of the whole string at any moment in time, right? So that's our goal. What we're going to assume is that this function is actually the product of two functions. The product of a function x that's only a function of x, and the product of a function called t, which is only a function of time, right? And if we do that, the second derivative of u with respect to t by the product rule, you don't even need the product rule. I'm going to write this as xt. X is only a function of x, t is only a function of t. We don't need to carry these parentheses along with us. So this is going to be x times t, the second derivative of t with respect to t, and then uxx is going to be t times the second derivative of x with respect to x, right? And when I do that, then I can substitute this into the actual wave equation. And what we'll get is we will get x t equals c squared t x x x. Let me clean up those x's. X, x. And this expression is really important because it's uniquely set up in a way that allows us to put everything that's an x on the right and everything that's a t on the left. And that's not hard. I just divide by t, and then I divide by x. So I get t, the second derivative of t with respect to time over t equals c squared times the second derivative with respect to x over x. And this is the crux of separation of variables. Everything that's a function of t is on the left, everything that's a function of x is on the right. And what's important to understand is now we do need to remember, oops, geez, that's a mess up. Now we do need to remember that t is a function of t, the second derivative of t is a function of t, x is a function of x, x is a function of x, and the second derivative of x is a function of x. So once this is set up, now we just think, well, what happens if I vary x? What if x starts at 0 and it goes to the 25.5? Well, we know that this function is a function of x, so that's going to change. Whatever it is, we don't know what that function is, but it is going to change. And this is the second derivative is a function of s, so that's going to change too. But this side is not going to change at all because it's not a function of x. X could change all at once, but the left side's not going to change. Likewise, if I change time, if I go to one spot on the string and I watch it in time, t is a function of time. T is a function of time, so that'll change with time, and t's second derivative is a function of time, so that'll change with time. But nothing on this side changes with time. So the point is that despite the fact that x and the second derivative of x both change with x, and despite the fact that the second derivative of t and t change with time, the fact that you're dividing them must somehow cancel out the effect entirely, because the only way this situation can exist is if both of these things equals a constant, right? Equals a constant. And that's the trick of separation of variables, because whatever that constant is, whatever, I can now write two ordinary differential equations. And the two ordinary differential equations I just solve using regular methods. So what are those two ordinary differential equations going to be? All right, so now I'll pause the video here. Let's see if take a little break. Do you normally stream these as glitches 0 and 0 stuff? Anyway, I hope you have fun recording these new series. Lots of fun with the wave equation, I imagine. Yeah, so glitches, no, I normally do not stream these. This is just an exercise in, you know, I got to admit, I don't know exactly why I'm streaming these. I admire some streamers out there. I like it. I like the streamers. I like watching streamers. So I kind of want to be one, so I guess that's part of it. But there's no real reason to. In fact, it kind of complicates doing all of this, right? This would all, I would be done by now if I wasn't streaming and worried more about the technology than it's more, streaming is more interesting if I'm talking to you guys about the things you're interested in. And you know, that is probably the better purpose for streaming. This is more of a, yeah, I mean, people may be interested in how I produce these videos, but certainly nobody who's interested in the main elements of the Helix project cares too much about the one-dimensional wave equation. This is awfully elementary. I would hope that this would be a relatively trivial review. Although I got to say, I haven't done it in a long time, so I'm kind of catching myself like, wait a minute, how exactly? Like right now, I've set it up so, okay, this equals a constant. Now I'm trying to think, okay, what is that constant's value? How do we say, is this the thing we called minus lambda squared before? You know, I can't exactly remember. I think it is, right? Because I think what happens is this becomes a second order partial differential equation. The answer, the solution for that thing is something like lambda. If we make it minus lambda squared, then it ends up being lambda, and then lambda gets fixed by the boundary conditions to be some fraction of an odd number. No, not even an odd number. It just becomes some it has to be fixed to be so that the boundary conditions work. So it has to be something like n pi over the length times x. I think choosing minus lambda squared is what we do here. Anyway, I'm going to do it and see if it works out. Yeah, thanks glitches and stuff. It's really about it's about humanizing some of the more complicated books that are out there, because it's just such an general relativity and some of those other things are kind of esoteric topics. um, it's fun to talk about them in detail if there's a chance. Um, I just wish I could do better production, right? I wish I had more time to do better production. But on the other hand, I think the people who do the best production out there are pretty much sticking to relatively elementary topics. And I should be careful about that because, I mean, I've seen some fascinating productions of some pretty sophisticated subjects like quaternions or something like that. Um, you know, yeah. So in some ways, I would say that uh, the it's tough to do. It's tough to imagine what a better production would be. I think you know what I think a better production would be, and I might go down this route. Uh, just opening up a paper or a textbook and literally reading it and opining about it as we read it, focusing on each expression, each doing a problem. I mean, literally walking through one of these more classic textbooks. You know, certainly the production would be better, right? Because you would have the physical material of the book in front of you. On the other hand, it becomes a bit dry at that point too. So I don't know. Speaking of accessible content, big thanks for producing all the content you've produced up to this point. Partially thanks to your help over the years, and I'm starting a PhD in 2 weeks. Oh, really? Where are you going to study, Glitches? That sounds terrific. First of all, thank you. First of all, congratulations. You will not be sorry. No matter where are you going to go to school, if you don't mind me asking. I don't want you to. Don't feel like you need to dox yourself, but I am curious because numerical relativity, that's a hell of a subject, right? That's University of Jena. Oh wow, I'm afraid I'm not familiar. I'm one of those guys who's kind of very provincial, I'm afraid. So don't take offense. I wouldn't know, but I definitely have many associates who study numerical relativity in great detail. Before LIGO was set up, numerical relativity, that was what their whole goal was. I remember, well, it still is, I'm sure. They really focused on. Well, I remember many people doing orbiting black holes, numerical relativity, and hashing out all of the tricky practical details. It's almost experimental. You might think that numerical relativity is a theoretical discipline, but it's like applied math. Obviously, well, I don't need to tell you, but it's a fascinating subject. I don't even know where to begin with it. When you get into it, Glitches, make sure you check back in and let me know how it's going. I'd be fascinated to learn something about it. I mean, I know something about it. I'd be fascinated to learn what is the current thing, right? Eventually you're going to get in the PhD program. You're going to, find yourself a niche in the university with a professor. He's going to have a project. You're going to find your place on the project. You're going to integrate with the other students, the postdocs, if there are any, the professor himself, the students that you will be teaching. It'll be a wonderful experience. But what I'm curious about is what is the actual problem you're going to be addressing in the beginning of your work as a student. And then I'd be really interested to know what problem are you going to be focusing on to get your dissertation done. Although in Europe, things are a little different regarding dissertations. So I'm curious about all that. But stay in touch, Glitches. I'd love to see how that goes. I'm just sitting here doing the wave equation. So I was thinking of talking about a numerical solution or demonstrating one on Mathematica where you simulate the string with a bunch of, something trivial like simulating the string with a bunch of springs and balls. And if you did that, you'd actually allow for a little longitudinal behavior of the string, right? Or you could play with ideas like strings with varying mass densities or something. Yeah, you should be excited about it. Look, I mean, how many people in the world have a chance to really dive in and get this stuff known. I mean, these are the most unbelievable, amazing thoughts humans have ever thought, and they're not available to everybody, which is a terrible shame. And it's not available because you can't get to it. It's not arcane, and it's only esoteric because the journey to understanding it takes so much time. Yeah, yeah. Well, separation of variables. It's separation of variables, spherical harmonics. It's all the same thing. Just diving into Sturm-Liouville theory from its essence is really something I find valuable. I think that's something I should do as sort of because that's actually a bit of a graduate level subject anyway. And I do have a classical mechanics section in my book about why does it move, right? My little book about the geodesics of a Schwarzschild space-time. And in that classical mechanics section, I should just do a whole thing on Sturm-Liouville and then produce a topical video on it. That'd be worth doing. That'd be worth doing. All right, so let's finish this up. Okay. Actually, I'm not quite sure where I stopped. Let's go ahead and I'll hit stop, and now I will record. So we end up with two ordinary differential equations. What are those two different ordinary differential equations? Well, the first thing is we're going to conveniently call this constant minus lambda squared. And the two differential equations are going to be t, second derivative of t, minus or plus lambda squared t equals 0. And the other one is going to be, let's see, it's going to be x, second derivative of x, plus, and then I think it's lambda squared over c squared, lambda squared over c squared x equals 0. Now I'll tell you why I'm pausing it right now. See, already I don't like this. And the reason I don't like this is I've got the dynamical, C is the tension over the mass, right? That's a dynamical feature, right? So the dynamical feature should appear in this equation. So what I've done is I should have divided through by c squared up in here, and then this statement would still be true, and then introduce lambda squared, right? The units would all be different, but the dynamical piece would land with the time, and this would just, the only constant on this side would be lambda. So so that's no good. So I'm going to delete the last minute and redo it. And I'm going to watch carefully to see if the stream screws up, because I'm changing the windows on my iPad. It seems like it's getting by okay. Okay, I think I'm back to normal. Yeah, no, if you can't see it on the screen glitches, then that means, well, no, in the final video it will be there. But I am a little disappointed that you can't see it on the screen. So here, let me see if I can find a way to fix that. If I grab the corner of the screen, I can shrink it, I can lift it, and then I think I can adjust. Yeah, there it is. See, I fixed that problem. Now it's a little small on the top. Let's see if I can fix that. So it looks like the top is getting cut off a bit, but and let's see. Yeah, okay. So thank you for helping me with that. That is a problem, and the problem is solved. Okay. All right, so I have this issue with the dynamics here. So what am I going to do? I guess I'm going to have to select and erase everything I've already done here. And I'll erase this constant. I'll erase that too. I'll repeat the word constant. And then I'll begin again. So what are the two ordinary differential equations that we're dealing with? Well, the first thing I'd like to do is I'm going to divide through by c squared so that the c squared appears on the left side with the time variables. And the reason I'm doing that is because c, remember, c is the square root of the tension over the mass. And those are things that have to do with the dynamics. So I suspect that we want to keep all the dynamics over with where the time variable is. And that will turn out to, in the end, help us. So we want to keep that up. Now, the constants changed a little bit because I divide by c squared, but a constant divided by a constant is just another constant. So what I'm going to do here is I'm going to give this constant a powerful, a strong identity. I'm going to call it minus lambda squared. And that is for convenience, right? So now I'm going to write down the two differential equations that are ordinary differential equations that result from this process. So I will write now down t plus c squared lambda squared c squared lambda squared t equals 0. And then x plus lambda squared x equals 0. Now, let's see if I have that correct. Okay, well, let's hope for the best here. And the resulting differential equations are these two guys right here. And the beauty of this is that these are really easy to solve. If you're familiar with ordinary differential equations, you can literally write down the solutions. So let's look at the solution for x first. I'll do that one in red. That solution is known to be some constant a, times the sine of lambda times x plus b times the cosine of lambda times x. And that is the function x of x. Now for t, right, it's basically the same thing. We got two constants already, a, b, so we'll go with I'll go with d actually. C can be annoying because it looks like a parenthesis. So d times, let's see, the sine of c times lambda times time plus e times the cosine of c times lambda times time. And that equals t of time. And so now with this, we have this here is everything we need to find u. Right? Now we can find u. And now you kind of see why, by the way, we chose minus lambda squared. Because the form of these differential equations, if you choose the constant to be minus lambda squared, is just very nice. You end up with lambda x in the argument of the trigonometric functions and a c lambda t in the argument of the cosine. If you had chosen some arbitrary constant like c, right, what would have happened? Well, this would have ended up being like the square root of C, right? We would have had the square root of capital C here. And that would have been just a touch annoying. Oh, and also this would have been a minus sign, right? So then we would have ultimately had to choose another sign to get this all right. So forget that. Anyway. So now I've paused it. I'm going to select the solution and then start working on the boundary conditions. Let's see. Select this, copy. Paste. All right, so with this in place, we just can simply write down u of x and t. This is our answer, right? U of x and t is our answer. And we know that equals x of x times t of t. And now we know that it's going to be the product of this red and green function. So I pause. And I'm going to paste this back. And I guess I'll erase the blue. And I'll erase this. And then I will take the lower expression and actually, yeah, I'll take the lower expression. Let me do this. Let me take the whole thing and shrink it. And then take the lower expression and move it over here. And then put in brackets. And then select the whole thing and move it up a bit. See if that all is on the screen. Okay. And this is our general solution. We call it a general solution because we still don't know A, B, D, and E. But the truth is that I could take this general solution and I could plug it back into the wave equation. U t equals c squared u x x. And you would get this to be true, right? That would be true. The second derivative of this with respect to time is equal to c squared times the second derivative of u with respect to x, even if you don't know what a, b, d, and e are. However, we're going to now calculate a, b, d, and e based on our boundary conditions and initial conditions. Actually, we have three things that we don't know. I'm sorry. Let's get it clear. We have 5 things we don't know. We don't know A. We don't know B. We don't know D. We don't know E, and we don't know lambda. So that's the problem. So let's attack them sort of one by one. All right, I'm going to erase this now. I've now committed myself to attacking these things one by one. So, all right, so let's see. The boundary, what should we do first? Boundary conditions? Probably, yeah, of course we got to do boundary conditions first. So boundary conditions, x, u must be 0. Okay, all right. So we're dealing with a guitar string. So u of 0 of t has to be 0. U of L of t has to be 0. Okay, let's do that one first. Okay, so the boundary conditions. What do we mean by the boundary conditions? Well, we've got a string and it's got some movement. We know here's the bridge and here's the nut. But we know that the string never moves off of the bridge and off of the nut. It's fixed there. On an ideal string, it's fixed. So we know that U at the bridge, well, let's see, U at the nut, at the nut, x equals 0, and at the bridge, x equals, well, x equals the length of the string, right? Now, our guitar, the length of the string is 25.5 inches for an awesome Stratocaster style guitar. So we know that when x is 0, it doesn't matter what time it is. It could be any time t. This function has to be 0. And we know that U at the end of the string where the bridge is, which is L, so we could modify this equation for the poor Les Paul players, right? L of t is going to be 0. That must be true always. So this means if you look at our expression here, t can take any value. Whoops, look at this. Oh yeah, so t could take any value. And notice this doesn't change with x. But here is where the x piece of U is all encoded in this section. So when U equals, well, when x equals 0, then cosine of lambda x becomes cosine of 0, and sine of lambda x becomes a times the sine of 0, right? But we know that the sine of 0 equals 0, and the cosine of 0 equals 1. So for x to always be 0, I'm sorry, for the displacement to always be 0 at the nut, this term has to always be 0. The problem is that at the nut, cosine of lambda x is equal to 1. So this piece always equals b. So in order for this whole thing to always equal 0, this side would have to always equal minus b somehow. And that's really not possible. So what we learn from this is that b, let me do this in blue, b must equal 0 to satisfy this boundary condition. And now we have to figure out what's left. We have lambda left, and this guy has to always equal 0 at x equals 0. But the sine of 0 is 0. So a is not determined by this, but b is. So that's really good. So we got rid of that. But now we look at the other boundary condition. At the bridge, we have the same circumstance. We already know b is 0, so we only have to focus on this. So when x equals L, this piece is going to be sine of lambda times L. And this is times the number a. Sine of lambda times L has to be 0. And the only way the sine of lambda times L can be 0 is in the circumstance when lambda equals n times pi divided by L. Because now if lambda is n pi over L, then the function itself has the form a sine n pi over L times x. And when x equals L, you get sine of n pi, which equals 0 for all n. But notice there's two really important things here. N is an integer. And in fact, we're only going to consider the positive integers, right? N is an integer, but it can be any integer. It can be any integer. So these two boundary conditions have told us two things. One is that b equals 0, and the other is that lambda is some integer times pi divided by L. So let me clean this up and include those facts. Okay, cleaning up this thing, I put it on pause again. So sometimes I decide to change erase everything and then and make changes, because you can always rewind. Sometimes I like to leave everything on the screen, but in this case I'm going to erase everything. So I'm going to erase this, and then I'm going to write, oops, do it in black. That's not good. A sine n pi over L x. Okay. All right. I think we're ready to go. All right. And we will start up again. Let's see, I need to get this U on screen a little bit. Maybe I should select all of this, move it over. And this is what results from applying these two boundary conditions. The entire first expression for x has been reduced to a, which is still unknown, times the sine of n pi over L of x. Now this is what lambda is. Lambda is this thing, n times pi over L, and it will work for any n. So this fact is important for two reasons. The first is that lambda shows up over here too. So wherever you see lambda, you replace it with n pi over L. So these two sides have been greatly simplified. So the time piece has also been greatly simplified based on the boundary conditions of the string. So I should be replacing lambda over there also. And now I pause it and I will do that. We will write this side as d sine c n pi over L, cn pi over L times time plus e cosine cn pi over L times time. And there you have it. We replaced lambda here with n pi over L. And remember, there's a c there too, the dynamic variable, the tension, the square root of the tension over the mass density. That's what that little c is. So now we have A, D, and E to contend with. Now notice the other thing is, no matter what integer value of n I use, this equation will satisfy the basic wave equation. This guy right, where did I put it? Right here, right? It'll satisfy the wave equation. So I still have three unknowns, but every value of n will satisfy it regardless of what the unknowns are. And the reason I'm saying that is because for each value of n you choose, you could have three different unknown constants a, d, and e. And therefore, each of those constants has to be indexed by n. So you kind of know which solution you're dealing with. You have n different solutions, an infinite number of solutions. And that's really kind of important. So even here, when I write, now that I've identified that, I haven't really written the most general solution, because the most general solution would be a sum of all of these solutions. But now when I've asserted n, I've picked out one possible solution of any one by just replacing n with some other number. So now every one of these things has to be indexed by n, right? So I have found the nth solution to the wave equation. But if I found the nth solution, I found them all because I just keep changing n. And that's really, really important here, because each of these solutions we're going to call a mode, or in the language of music, we're going to call it a harmonic, right? But so now we're solving for the nth mode. the nth mode. And n could be 1. It can't be 0, though. We don't want it to be 0. We want it to start at 1. Okay, so now we have, let's think a little bit more about the rest of the conditions here. All right, so now I'm trying to remember what is the condition that we're going to use to get rid of. What is the condition that we use to get rid of this term here? Let me think. What was the condition here? What is it? It's a boundary condition. Have I used these up already? U of L of t for all time. Yes. Oh, I think. Oh, you know what it is? There's another condition. I think I need to say that at the initial condition. Yeah. It's the initial condition, but I forgot an initial condition, right? I forgot the initial condition that the velocity at the beginning is 0, right? And that initial condition asserts that yeah, I'm pretty sure that's going to work. I'm going to actually create a new segment here. All right, so now these were the boundary conditions. The boundary conditions is what these guys were, and that really zeroed in on the structure of this. But it also got at the structure of t too, because it figured out what lambda was, right? So now we're going to look at the initial conditions. So I'm going to erase this. And the initial conditions is what is the string doing when we start the problem, when we release the string. So we have to kind of choose that, right? We have to say, what is the value of u at for all x, but at t time equals 0, right? That's the initial shape of the string. But the string can not only have an initial shape, it can have an initial velocity, right? So the time derivative of u along the string at time t equals 0, we need to assert both of those things. So for our initial condition, for a guitar string, right, if you dig into the pick, you pull it up about 1 millimeter, right, then the initial condition is going to look something like, it's going to be 0 at the nut, because it's always 0 at the nut. It's going to go up a little bit, and then where your pick is, and then it's going to drop until it hits the bridge, right? Remember, this is the nut, and this is the bridge, right? And this distance is the height that you're picking it. We'll call that h, right? So the initial condition is this shape, right? This shape right here is our initial position, our initial condition. But also, you're not throwing the string down. You just release it. It's motionless, and then you release it. And when you release it, it starts moving. So the initial velocity is going to be 0. The initial shape is going to be this thing, right? Good. So now, if the initial velocity is 0, let's look at our function un at time t equals 0. And what does it look like at time t equals 0? Well, this term at time this is the function un at time t equals 0. I want to enforce, this guy looks easy to handle. So we need the derivative of this with respect to time at t equals 0. So let's calculate the derivative of this with respect to time. All right, so now I've got to actually do that, don't I? So let's see. It's going to be an sine n pi over L x. And then the derivative of this is going to be, the derivative of sine is cosine, so it's dn, and then times c n pi over L cosine c n pi over L t. And then it's plus, no, it's not plus, it's minus, right? It's minus en cn pi over L sine cn pi over L of t, right? Do I have that right? And that is u n t. Okay, let's see. It's a little big. Shoot. Let me take this, move it in a little bit. See if that helps. All right, and this is the derivative we seek. I'm taking this, I'm taking its derivative with respect to time. Obviously, that's just a constant as far as time is concerned, right? So this guy, sine, the derivative of sine is cosine, and then the chain rule pulls out a factor of cn pi over L. So it's d cn pi over L times cosine cn pi over L. And then this one, the derivative of cosine is minus sine. So there's the minus sign. It's right like that. Now, our condition is at t equals 0. So I plug in t equals 0. When t equals 0, this becomes 1, right? When t equals 0, this becomes 0. So at t equals 0, this part doesn't contribute at all, right? But at t equals 0, but at t equals 0, this part here contributes. This ends up being 1, right? So this guy here is left over. So the only way this thing can be 0 at t equals 0 is if dn equals 0. So dn has to be 0. And that's all we need to know. Now we've gotten out that we know dn. Now that we've gotten through this, dn is 0. It doesn't tell us anything about en, but dn is 0. Okay, so with that knowledge, we can go back to our general mode and we can get rid of this term because dn is 0. So that term goes away. Only for the initial condition of a motionless string, by the way, right? You have to have a string that starts with no velocity, right? And then you get this nice simple expression. You get this nice, in fact, it's so small now that I can actually fit it on one line, right? And that becomes your nice simple expression. Now what have we got? So this is still true for each mode n, right? There's n different possibilities here. When I say n different possibilities, it sounds like, you know, you pick a finite number n. No, there's an infinite number of possibilities, one for each integer. But notice these two constants, an and en. They're now factors in front of these two numbers, so they can be combined, right? You just take en, you bring it out front. Let me erase that a little more carefully. You bring it out front, and now you combine it with an, so you have an times en, and we just rename that an, right? So there's really only one constant that's unknown right now, and that's this constant right here. We still need to figure it out. It's actually critical that we figure it out, but it's unknown right now. Okay, but look how far we've come. We've now got an expression. We've got an infinite number of functions, u of n of t, all that satisfy our guitar strings wave equation. And the final solution is going to be some sum of these, right? The resulting solution is going to be a sum of all of these. And let me show you quickly why that is. So now I got to pause and just get rid of all this stuff here. Let's see, I'll get rid of this, delete, and I'll get rid of this, delete, like that. Right. So now I'm going to, what I want to do now is I want to explain why is it that the true solution is equal to a sum of these, right? So the way I'm going to explain that is I'm going to say our equation is, whoops, let me do this in black. Our equation is u t t minus c squared u x x equals 0, right? So if converting this back to differential operator form, I have this minus c squared this, right? And I'm applying this to the function u. So say I applied it instead of, and u definitely solves that to be 0, right? That's what u is the solution of the wave equation. But obviously, it kind of goes, is it obvious? It should be obvious. Well, it's obvious. Who knows what obvious is? But if I take un and I add it to um, where they're two different integers, I know each one solves it separately. But it turns out, of course, this is a linear operator. So we get d squared dt squared, the second derivative of un plus um, minus c squared partial squared dx squared un plus must equal 0. And being a linear operator, each of these is going to break down into d squared dt squared un plus del squared del t squared minus c squared partial x squared un minus c squared partial squared x partial x squared that whole thing has to equal 0. But we know that this minus that equals 0 and this minus this equals 0. So clearly the sum was a solution, right? Okay. Yeah, that was kind of obvious, wasn't it? So I want to now quickly go through that. All right, let me erase it and just do it again live. Okay, so we now know two things. We know that un is a solution to this differential equation. I'm going to write it slightly differently. That if I take this differential operator and act on un, I will get 0. Right? I will get 0. And now it's also true that I can now show, or my plan to show, that if I replace un by un plus where is another solution, I will also get 0. And you can kind of see this is all linear is the point, right? I can bring this operator inside here one by one. I can attack un first with it and then second. I can distribute this as a linear operator inside here because derivatives are, that's the rule for derivatives, right? The derivative dt of the function x plus the function y is dx dt plus dy dt. We know that from basic calculus, right? So the same is true with second derivatives, right? Second derivatives are also follow the same rule. So I will erase this. Do this little digressions. When I do the little digressions, I have to pause and erase them. And what do we get here? So clearly, this operator, when applied to un, just gives me un. I'm switching up notations here. Minus c squared un xx, and then it's plus right? That's the letter m, tt minus c squared um xx, and that does that equal 0? Well, this plus this is the wave equation. Oops, sorry. Yeah, well, this is the wave equation for un, and that, of course, equals 0 by definition. Un is a solution of the wave equation. Likewise, m was assumed to be a solution. So the point is if you take any two of the modes and add them together, regardless of what this constant an is, because that doesn't even matter, that can be anything, you always have a solution. So if we were going to write the most general possible solution to all of this, what would it look like? All right, so now I will erase all of this. All right. Okay, let's see. So, well, the first mode is u1 of x and t. The second mode is u2 of x and t. The third mode is u3 of x and t, etc., 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 till you get to any number, right? Let's call it, well, n of x and t, and then you keep going, right? So if you add up all of these together, what that sum will always be a solution of the wave equation, always. So the way we can write this down is the sum from n equals 1 to infinity of un of x and t. That is what our function actually must look like. Our function must be this infinite sum. So now we have a really good grip on the answer. The answer, our function that tells us exactly the shape of the string, for all time and all positions of the string, is this infinite sum of these modes that we calculated. And each mode looks like this. But each mode comes with its own constant. And we still haven't nailed down what that constant is. And that is the last and the hardest part of the entire analysis, is that final constant. The final constant is ultimately determined by the initial shape of the string. So the initial shape of the string was this very askew triangle where this height is very small compared to the length L, right? I've exaggerated it in this picture, but with the bridge over here and the nut over here, this is our initial shape of the string. And in order to calculate these ANs, right? In order to calculate these constants, we need to arrange a sum of all these modes and give each mode its constant, right? And those constants and that sum have to add up in such a way that u of x at 0 is equal to this shape right here. So we have to describe that shape. And what's the mathematical description of that shape? Well, the shape has a slope, a constant slope here. It's a very simple shape, so that's lucky. That's helpful for us. So that's lucky. So this shape has a constant slope. So what we want to say that u of x and 0, it's going to be, oh, there's another number we need, of course. We need to know where we plucked the string, right? Where did we pluck the string? So that distance of plucking the string, I got to give it a symbol. Let's give it a symbol little l. I think that that'll look pretty good. Little l. No. Better not. Because if I say the word L, of course, nobody will know what I mean. Let's call it R. Right? So the slope of that line is h over r, and h over r times x is the position of the height of the string from between when x goes from 0 to r. So as long as x is less than r, right? When x goes from r to when x goes from when x is in this final regime from r to capital L. See, that would have been from L to L. If I had chosen r to be L, it would have been from L to L. So that's no good. So when it goes into this last regime, then we have a different, so when x is greater than r, the function suddenly changes. And when x is greater than r, we get we get this. This is what we get. We get when x equals, so this works because when x equals L, it's 0, right? So when x finally gets over here to the bridge, the displacement is 0. But when x equals r, then x minus L and L minus R cancel. They cancel with a -1 though. So I think I want L minus x here. I don't want x minus L. I just want L minus x. Right? So now when x equals r, you get h, right? Which is exactly what you should get. So this is sort of a step. This is a step function, right? Well, not a step function, a piecewise function, right? This is a piecewise function. I don't need to write that. So this is a piecewise function. So this is the true initial position of the string. So we need it to be that this sum, this infinite sum here, when I set t equals to 0, right? When I set it so that t equals to 0, that infinite sum has to have this precise shape. And that is where we introduce the idea of the Fourier sine series. Okay, well, let's see. That might be it for me for now. I think I've made some progress. I've practiced a bit using the streaming system. That's cool. Oh, I noticed, look at that. Again, my reflector is no longer it spontaneously changes. I've really got to figure out why that is. But I think that's all for now. I've done some rehearsal on practicing a lecture or producing a lecture live. I don't think it's particularly interesting content, but that's the beauty of YouTube, is you can just walk away and you don't have to. This is dragged in 8 of you for the duration of this. Thanks for hanging out. Yeah, glitches. I noticed the edges are still cut off. Oh, wait a minute. Yeah, the n equals 0 case. Yeah, n can be 0. It's just, it just doesn't. it just doesn't, it's not usually expressed that way. You usually don't include it. You just sort of set the equilibrium position to be 0. So um, yeah, in quantum mechanics, you see Fourier analysis. The thing that makes this nice is you have boundary conditions that are not from minus infinity to infinity, right? Um, yeah. Hello, Doashir. You're welcome. That's my pleasure. I'm just experimenting with a few things today. Experimenting a bit with the stream, experimenting with this lecture, and I'm going to pause here and then do the Fourier sine series part later. This whole thing isn't very precise, I got to admit. What I'm going for, though, is not the kind of precision that you're used to seeing in the other videos. This is much simpler material, and it's meant to be a little bit more gimmicky, although it'll be hard to explain why that is to you guys now. But when you see the finished product, you might get a sense. It's going to be some sort of comic, gimmicky thing. Anyway, thank you all for watching, all 10 of you. And I'll probably be popping on and off a lot this weekend, kind of perfecting this. And we'll talk to you soon.